All right, thank you everyone for joining us today. We have a project presentation by none other than our fellow, Nick Murzin. And this is kind of on the heel of what was done during the summer school, a bunch of very interesting projects, and Nick had his own one that was a community post that has gone live, and he's here to talk about it today. So Dugan and myself will be watching and learning from some more quantum related research. So yeah, with that, Nick, please take it away.
Yeah, hold on. Yeah, there it is. Maybe we should post a link on the community from the community forum of this post. So this is like a post I was doing during the summer school, the Wolfram summer school, which is like mostly inspired by other students doing something. So I kind of thought that maybe I should do a project of my own, just on the side of actually mentoring other students and helping them with their project, but also like do some quantum related project related to topics that have been interesting at the moment. Already kind of starting to forget about what this project is all about. We should have done it like 2 weeks before today. So I haven't reminded myself about what it is all about. But it's like basically the topic is about Bohmian computation, which is like some kind of extension to the Bohmian mechanics, which is one of the interpretations of quantum theory and quantum mechanics, which is like I have a short crash course on the actual Bohmian mechanics in the post, which is like a lot of just mostly a bunch of like visuals and of course a few formulas, which is just like a Schrodinger equation and how you can convert it to the Bohmian mechanics in the usual way. You just like take the usual conventional Bohmian Schrodinger equation, where you have a wave function, right? And you just substitute the wave function in its polar form, right? When you have real amplitude and phase, right? And when you do it, you essentially can write down the wave equation, the Schrodinger wave equation, as two real equations, which one be like a continuity equation of the density, which is just like an inverse gradient of the current, probability current in this case, and the quantum version of the so-called Hamilton-Jacobi equation, which is like almost the same as the classical case. For those who actually studied theoretical mechanics, they have all of this formalism like Lagrangian, Hamiltonian, and then you go from Hamilton-Jacobi equation, which is like usually at the end. So I myself don't remember studying it. So so maybe it's like very not really popular formalism for theoretical mechanics, but it's essentially like this kind of equation is studied in the classical mechanics just without this term. Which this term is actually the quantum potential. The quantum potential. So that's purely quantum thing, right? This is just non-local force, essentially potential, which then leads to some quantum non-local force that actually acts on particles. So you have some particle moving along guided by the wave function, right? And you know how the continuity equation describes this flow, but also each particle also moved along with some kind of additional force acting on it, which is this quantum force, which is non-local. But you also can interpret it in some kind of fluid dynamical way. There's like a nice additional topic related to Bohmian mechanics, which is stochastic mechanics and hydrodynamic analogs that also try to look at the same kind of mechanical systems, purely classical, which is a completely different scale from nanoscales of particles to the actual macro scale, micro scale of actual waters, which is like droplets of liquid jumping around on some kind of bath, which is dynamically fluctuating with some frequency, which is like related to constant frequency of the particle, maybe by a factor.
So can you explain this visualization here? Is this a natural process, or is there some kind of like deliberate frequency or something that's injected into this scene?
Yeah, so this is like the whole lecture course, which is just ended this spring by the guy called John Bush from MIT. There's like no video recordings, unfortunately, but you can find a bunch of lectures by this guy if you're interested in the topic.
I think Veritasium did something with this.
Yeah. And also, like, it was popular like maybe 7 years ago when this guy came up, and there was this whole controversy about this particular types of experiments that they can mimic all the quantum mechanical effects. Right, but turns out there's no contradiction. It's just you have to think about it in a proper way. But the point is that people learned maybe around like 15-20 years ago how to do these experiments with some droplets on a liquid. I think it's like a silicon or something like that just vibrating on some kind of audio device with some frequency, and you can then induce some fluctuations which just become a droplet, and it just can walk around on this liquid propagated by its self-induced wave. So the droplet jumps around producing a wave, and this wave also guides the particle. Right?
So interesting.
Right. So it's a little bit different from the Bohmian mechanics. The difference is that in Bohm mechanics, it assumed that the pilot wave affects the particle, but there's no feedback from the particle to the wave on the wave. So there's no feedback. But here it's like you have just a particle. It produces a wave by just jumping around on the liquid, and this wave also guides the particle. So they kind of tangle together. So that's why this kind of hydrodynamic quantum analogs and all this stochastic dynamics is an extension of the Bohmian mechanics, right? You just a natural continuation of it, and also can be studied with these classical systems by just studying these droplets. Why the single droplets or pairs of droplets, they can entangle with each other. There's still it's still in some early stages, but there's some nice experiments reproducing like double slit experiment, and even some theoretical suggestions, I think, at this point only, like how to reproduce Bell inequalities by just entangling these droplets together. So
I wonder if you could make a quantum computer from vibrating droplets.
Perhaps. Perhaps you can. Maybe it's going to be very slow because it's like the time scale is a completely different, right? We assume that like quantum theory is like some kind of limit, right? So it's like very fast fluctuating thing, but actually there is some limit to actual how fast it fluctuates. And even usual quantum systems maybe have these limitations underneath, and the quantum theory is just the actual limit, but it doesn't actually realize it in the real life. It's like we assume that it's like actual wave amplitude, quantum amplitude wave, but it actually is some kind of finite limit of just electron fluctuating on a contact frequency or something like that. Not like, I don't know. It's like, let me just, I have more analogs to the quantum computation. Maybe this kind of thing will become clear, right? But this is just so we continue on this Bohmian mechanics crash course. Yes, there's like a natural extension to hydrodynamic analogs and fluids, right? But like classical, or I would rather say not classical, but something like conventional Bohmian mechanics deals with just definite trajectories of particles. So it's like if you want to describe double slit experiment, this is like in the classical motion, they just have straight trajectories. There's no force acting on it, right? Even there's just if you pick a particle, it just moves along after the slit. But the quantum particles actually, because they have some pilot wave guiding them, this pilot wave introduces this additional force. So they have some you can see that they deflect from other trajectories, and it seems like there's an actual force acting on them, so the trajectories are not straight, right? So and you still can see the interference pattern, so you can all the parts. Yeah.
So what causes those gaps? What is that effect called?
Well, this is just that's, you can call it interference, right? That's the usual interference pattern that you see in the double slit experiment. But here you see how it realized with the actual definite trajectories of each particle. So you assume that you don't know the initial position, right? You can assume that it started here, or here. It's like, but it's every time it's definite. So all the probability comes from our ignorance about the initial condition. So you don't know where it starts, but as soon as you know, fix the initial position, the trajectory is going to be the following, right? For example, if it actually went through the left slit, it's never going to slide to the right side of this picture, right? It's like they actually, like, this is like acting as a barrier. All the trajectories starting here is always on this left side of the string. They never cross each other.
So that's a wall, I guess, that they're bouncing off of.
Well, there's no actually a wall, right? There's no wall, but there's, like, you can say it's an effective wall because the pilot wave kind of prohibits traveling the left particle to the right side of the screen, right? by this quantum force, right? So this is just the double slit experiment. Also, if you just want to explain how some internal degrees of freedom work, like spin of the particle, you can also explain it by just definite trajectories. And now the actual internal degrees of freedom, like spin, become a contextual property of the apparatus yourself, of this non-uniform magnetic field. So if you still don't know the initial position, but depends where it is, it's going to end on different locations on the screen and they're going to be quantized. So it's always like either left or right. And all the trajectories, you can see how they actually reflect from and how those different trajectories behave. So basically, Bohmian mechanics tells that there is no internal degrees of freedom and they are realized by some contextual mechanism. So it's like you can say that this spin is just an effect of the position itself. So the definite property, always the definite property, is just the position allocation of the particle in space. Right, and that's kind of the first thing we're going to change when we go to the quantum computation to define the discrete systems, not this continuous systems of quantum mechanics with particles and then definite position in space, and just going to try to describe spin or polarization of the particle by just internal degrees of freedom. Right. So this is we have more examples like quantum tunneling, and just you can find there's all the links in the papers, and there's a nice in the community forum, in the Wolfram community forum. There's also a nice post how to explain. I think that's community forum. Does this link work? It looks so bad. Basically, it's a Klaus von Bloh post about how to compute the trajectories in the hydrogen atom. So you still have the definite trajectories of electron. So it's always like looks like how this planetary model of the atom, but in Bohmian mechanics it's actually true. It's a little bit different because, for example, some ground state orbitals, I think the trajectory is actually stationary, so electron is not moving. So it's not actually rotating around the atom, it's literally not moving in the ground state. But when you introduce spin, then it starts moving. So there's some subtleties to that. But you can explain all kind of quantum system by just definite trajectories of particles guided by the pilot wave. All right. So this is like an introduction to Bohmian mechanics, some simple crash course. But the project was mostly about how you can apply the ideas of Bohmian mechanics to quantum computational systems like qubits, quantum circuits. Right. So obviously we're going to use our Wolfram quantum framework for that, and we're going to start with a simple qubit, just by how can we describe the acting on a single gate on a simple qubit, and how we can describe this action, quantum action, by the same ideas, similar ideas. So, for example, we generate some qubit in the zero state, which is just on the Bloch sphere, just a vertical vector, and apply some rotation by 60 degrees. Right, like this. So this is like a simple rotation gate of the qubit in initial state. So okay, so what does it mean? First of all, the gate is like a discrete operation. Usually, it considered like a discrete operation, just flips the bit to some other position on the Bloch sphere. But you can naturally extend this idea and analytically continue it, so to speak. You can turn your unitary gate, which is just a matrix, to a Hamiltonian, and just look at it as an infinitesimal rotation instead. So an actual, you can see even this is like a discrete unitary gate applied. You can still look at it as there's a Hamiltonian acting in it continuously, and the actual qubit evolves like this. So it's actually rotating continuously from one position on a Bloch sphere on your Hilbert space to another position, right? And when you have this kind of picture, you can also continuously look at them as mostly already as a trajectories, but those trajectories are in this discrete space, because particle now doesn't have a position like this position in three-dimensional space with x, y, z coordinates. They just can contain two discrete values, either 0 or 1, up and down, right? We fix the basis for now. I'm going to mention what changes when we're not going to fix it. But if you change like the basis, like for example the z direction or 0, 1 computational basis, now the particle can occupy either 0 or 1 state. So just discrete but definite position, right? But or value. And you can start asking questions. Okay, now that if we want to describe the system in this definite deterministic way, so almost deterministic, how you can do it? Because it's a definite discrete state, now you can't really describe it by a continuous equation, like we had this continuous equation of a trajectory. Now you have to actually introduce some stochastic dynamics, because the only way to dynamically change a discrete value from 0 to 1, 1 to 0, you have to do some actual discrete jump. So you can't really describe it by a continuous equation. You have to describe it by some kind of stochastic matrix, for example. So that's like a probability table of jumping from one state to another state, right? So for example, arbitrary 2 by 2 stochastic matrix, because we have two values, can be formulated like this, right? And if we know the initial probability of the qubit being in 0 and 1 and the final probabilities of 0 and 1, we can actually fix one of those values, right? For example, like you can compute that for this particular example, the p is p over 4, right? It has the probability at the end being like 25% of changing the state, something like that. But it's not allowing to completely fix the stochastic behavior from just initial and final probabilities. There's some 1 degree of freedom, this q value, which is unknown. So the actual trajectories, which we just can describe a probability of the particle or qubit being in 0 and 1 state by an actual probability, is kind of varies. So there are many trajectories by this probability the particle can take. So at each point in time, in this unit interval of time, the particle can be at state 0 with different probabilities based on different trajectories. So it's not fixed. The dynamics is not fixed. So it can change its probability in a different way, because we only fixed the initial and final one, right? So how can we fix it? So that's the first question I asked for this project, right? There's some works, like even by John Bell himself, by trying to extending Bohmian mechanics to lattice theory and quantum field theories, when you discretize space, and then you can say, if you discretize space, how the actual dynamics changes, right? Which is essentially what we do. You can say that our discretization is very primitive. We just have two states, right? But you can say that it's just our space is very small, right? But so we can apply the same kind of ideas that Bell did. So we can compute. So essentially, you can compute the probability current from one state to another by just by our Hamiltonian and density matrix, right? And after computing the current, it's like a probability current of changing, pushing on the particle. It's almost like some kind of force acting on it already, but it's like just an actual fluid of the pilot wave. Well, this is just a wave function now, discrete wave function of the qubit acting on a qubit, trying to push it from one state to another, right? In this, so now it's like actually inverse. So the current from 0 to 1, you can compute it by this, and if it's just two values, then the inverse qubit is just the negative of that, right? So you can compute one only. So you only require to compute one current from, for example, from 0 to 1, and from that, there's like a bunch of different ways of computing it. I guess we can skip it because it has always this kind of form with some natural frequency given by Hamiltonian. But from the current, you can actually compute the probability of jumping. It's almost like applying a probability. What's the name of it? Like joint probability rule or something like that. When you can treat the jumping probability as like a conditional probability. This is the probability of being in one, but if you essentially clamp the current so that it's not negative, right? Because it can be negative. if you compute it by that formula, you clamp it so that it's positive, then you can compute the probabilities of jumping, conditional probabilities. What would be this? I guess it's not probability, it's probability density, because you can use it to compute what's the probability of jumping in some small unit interval of time. So you actually have to multiply this by delta t to actually compute the probability of jumping. And then I just made a bunch of integration things. For example, also when you compute the density, you can see that there's actually a negative component, negative density of jumping from 1 to 0. So it's actually ignored, right? So after you clamp it like this, and then you can do some fancy integration things. You can basically assume that, okay, we have the density, we can multiply it by the unit small interval of time, what the actual probability of jumping for the whole unit interval, right? You just essentially multiply all those probabilities together, and this is like not jumping before that. Essentially, you can interpret it. You either jump in this unit interval of time, like this tiny one somewhere here, and not jumping before that. So it's like you can formulate the probabilistic problem like that, and then you just integrate this expression, sum over it, take the limit, and you get this kind of integral. So this allows you for this simple example, we can actually compute it exactly. So we know the probability of jumping from 0 to 1 from after the whole unit interval of time passed, right? And then this allows, so this is like the natural way of actually describing what happens to this qubit, definite state of the qubit on this whole interval. And this is actually fixes this stochastic parameter that we just couldn't do when you just introduced imposed initial and final probability distributions of being in one particular state. So among all of the possible trajectories of probabilities, this, for example, for this case is the actual Bohmian qubit travels along this trajectory. So that's a lot. So we solved dynamics for this simple rotation. Okay, so now we can describe this rotation as actual qubit being in particular state. We ignore the pilot wave. If you just focus on the actual definite state of the qubit, then the probability of being at every moment in time, at state either 0 or 1 is the following, right? So we just fix the dynamics in this way. All right, so this may be.
Why did you need to fix the dynamics? What was the necessity for that?
No, this is just like this just was kind of natural questions to question to solve.
Okay. Is it possible to do that?
Yeah, it's like it's just a kind of motivation was, okay, I want to describe the dynamics with just a stochastic matrix. Just okay, definite qubit, definite state of the qubit just jumps around. How you just describe a single matrix, right? If you actually know what it is, you can't really fix it, right? Unless you actually look at the intermediate pilot wave and how it actually pushes. And there's some subtlety on how to distinguish, for example, between the probability of being in a definite state and the density of the of the wave function. There's slightly different things. I have I think after example of the general qubit, maybe just quickly go for it. I have a comment on how to actually treat those probabilities and densities, because they're actually different things, and how you should actually look at the sortatic qubit. But okay, this is just quickly go through a more general case when we just not a simple rotation, but some random one of the random qubit, when your current is actually more complicated, when it's actually oscillates, not just always positive. It can like oscillate, and you can change the direction essentially multiple times during this unit interval of time. You can do the kind of same kind of thing, right? But when you clamp it to actually compute the probability density, you see that the probability at some point either non-zero for jumping from 0 to 1 or from 1 to 0. So in a way, in order to fix the dynamics and compute the probability at the end of the time interval, you have to take 3 integrals in these 3 different regions. So it starts to be very complicated, but you can still do it precisely. You just determine like all these crossings, integrate that, and you can still fix, and all of that is just doing that essentially. you can still fix the dynamics and the trajectory even for these complicated cases by just integrating over multiple regions.
And you've done all of that basically in code. You didn't write out the mathematics side of it.
Yeah, like for example, like this code is mostly it's the most complicated code of this of this post. It's just like given a quantum operator and a quantum state, what was the qubit matrix, stochastic qubit matrix essentially that describes the 2x2 dynamics of the qubit, right? So that you can just use it, which is solved by doing this integration. Like here, it's like solves for 0 when it crosses the axis and all that, and then determines all this in multiple intervals, what are the signs of those intervals, and then actually doing this integration of exponential. So it's kind of precise numerically, right? But you can still compute this matrix, and it fixes the dynamics of the qubit for arbitrary Hamiltonian in initial state. So, but yeah, this is like a comment about, because we chose a particular basis at the beginning, like the computational basis of the qubit being either in 1 or 0 state, but you can do the same kind of thing for any basis, right? This is, you can just transform it and you essentially can determine the dynamics in any basis. Okay, here's like another comment about what this actually stochasticity, stochastic matrix is useful for, right? How one can use it and describe it, because when I say stochastic dynamics, I usually assume that you can simulate it by some kind of procedure, some probabilistic sampling, right? So in a way, it fixes this procedure of how the qubit changes at every moment of time, and for example, or multiple qubits changes. So in a way, you describe an ensemble of qubits, or in a way, you can describe a qubit as an ensemble of particles, right? You just sample, because every initial state just fixes the probability distribution of qubit being in some particular state, depending on the basis, and you can just sample it. Right, sample is just like 0, 1, 0, 1, 0, 1, and just have some distribution, right? And then the stochastic matrix here just determines what would be the probability of jumping from this state of the current state to the different state, and you just resample every time, and then you essentially, if you compute the final distribution, final histogram essentially of those samples, they should follow the same distribution if you just use usual quantum theory formulation and multiply matrices together and apply the Born rule, right? All of that. So essentially, we just change the dynamics of the qubit from the usual quantum mechanical operations, like applying unitary transformations and squaring the amplitudes to get the probabilities. We're just starting with only probabilities, which is just our ensemble in a definite state, and then apply some stochastic matrix by just resampling it with some probability dictated by that matrix. Okay, that's how actually sampling works. All right. Okay. Any questions, comments this moment? At this point?
No.
Okay. So the next kind of set of questions is how you would extend it to multiple qubits, right? And essentially, because famously the Bohmian mechanics is non-local, right? Because of this non-local quantum force acting on a particle, changing its trajectory from the straight one to some accelerated one, right? In this particular computational finite discrete system, what is the analog of this non-locality and how you can show it explicitly, right? So, for example, like if you now have multiple qubits, for example, if you start with a absolutely arbitrary quantum state, entangled state, essentially that will describe multiple qubits, maybe entangled with each other in some complicated way. Like this is the state describes just some arbitrary entanglement between 3 qubits. And then how you describe dynamics over a second qubit when you apply some arbitrary unitary transformation on it, right? So in the same exact way as we did it earlier, what the dynamics of that second qubit when you apply to when it actually entangled to other qubits. So that's where non-locality arises, usually the Bell inequality, the Bell non-locality, because there are different notions of non-locality, but that's the different problem. All right. So essentially, how it changes the dynamics is that you have to consider now all possible contexts of those other qubits that your qubit is now entangled to. So for this particular example, if you have 3 qubits entangled to each other, then if you want to describe the dynamics of the second qubit, how it changes under unitary transformation, you need to consider 4 different contexts of all other definite values those other qubits can take, right? So it's either 0, 0, 0, 1, 1, 0, 1, 1, right? When you kind of fix those different possible states that essentially determine all the different contextual states, I call it just context states of our qubit of interest here, right? So it essentially determines 4 different contexts where the dynamics can happen that determines this local context for the second qubit, which is just some arbitrary mixed states in this case, right? And then you can just use the same function that I've defined previously for these different states in those 4 different contexts and determine different context, different stochastic matrices for all those contexts. So in a way, how you can look at it explicitly is essentially you can say that you can describe these dynamics now, but essentially this kind of multiplexer. It's like you computed 4 different stochastic matrices for all of those 4 different contexts, and you just applied them conditionally depending on that context. So now this circuit is not a quantum circuit, technically. It's only quantum because I'm using the quantum framework, but it's not quantum because it actually, like, this is not the wave state vector or wave function. It's just a probability distribution, which is just a vector of probabilities over 3 qubits, and this is just stochastic matrices classically conditioned on different values. So now, given this classical circuit that just describes how probabilities change from one step to another, you can describe how an actual probabilities of the original circuit can be recovered by just running this computation instead. So now we describe, so again, we just get rid of the usual quantum theoretic description using amplitudes and waves and just describe it using trajectories. But in this case, trajectories are just this finite discrete definite states of the qubit and how those changes probabilistically from, like, depending on the context and the actual initial probability distribution, you can determine the final probability distribution. So that's how non-contextuality and non-inequality is explicitly shown in this kind of computational Bohmian computational case. Yes. So okay. So this is another set of questions been answered.
I have a question on that. Can you elaborate a bit on, at the top you mentioned that there's like locality or non-locality, but in modern times it could be considered the word contextual instead. So
Yeah.
What is that rephrasing to contextual? What does it mean?
I think like mostly because non-locality can mean different things depending on the context. Again, pun intended. It's like usually non-locality was formulated by Bell, meaning by just like essentially what we usually call it now non-separability. It's like having this entangled state. If you can separate it as an actual qubits and a product of qubits, then it's not separable, meaning it's non-local. So like a Bell pair, right? If you have a quantum circuit with a Bell pair, I'm kind of out of practice, right? If you have a Bell state, I guess Bell state. This is like you can think of it as just this particle going to the left. This is a particle going to the right, right? And they can be separated in space, but they're non-separable because it's like you can't really write them as just 2 different states. Like, I don't know, just some random things on the first wire and on the second wire. So this is like you can't write it as two separate states like that. So they're non-separable. So you can't write it as a product of two states. So this is like a Bell non-locality, but also by non-locality we will usually sometimes mean there's some like some kind of signaling faster than speed of light happening, things like that. So usually now I think it's better to use non-contextuality, contextuality, and non-signaling, non-separability, this kind of arguments, instead of just saying that it's non-local.
Is it just because the word implies less ambiguity for people trying to comprehend locality? Yeah.
Yeah, I think so.
Okay.
but I'm not particularly sure. But
okay.
That's my take.
So how would you use the word contextual in this case with the Bell pair here, or the Bell inequality? Is it the qubits have the same context? Is that how you would use that term?
Well, here maybe I'm even confusing further, right, by calling this a context. But maybe this context is a bit different context by people, because usually what people usually mean by context is your measurement settings or something like that, like, right? And for example, if you have your usual setup of Alice and Bob measuring their corresponding particles in the Bell entangled state, they have some settings involved, measurement settings, measurement basis choices, right? And this is the context there.
Okay, so that's why it's a better word to use than locality, because just because it's local, you're kind of there's an implied context to that locality, but it's not quite the right word. I think context does make more sense there.
I mean, I think I hear because I made it's in quotes because because it's actually a different context. So I just couldn't figure out the better name for it. It's kind of makes sense to call it the context.
Yeah, it makes sense. Okay.
Yeah. Okay. So this is like a section about this. Okay, this is like a too complicated side question that I tried to answer. Maybe I don't go there. It's like maybe at the end is actually trying to formulate this system with some fluid mechanical analogies, like an actual stream of some underlying fluid flowing and different kind of velocities. But mostly this is about how to differentiate between the probabilities, as I said before, of actual qubit states being in some particular definite state, and the density of the pilot wave, right? Because if you do the same example as we did above, if you plot the density state, which is like the Born probability density, is like when you actually at every moment of time you take the pilot wave, the state, the wave function, and square its amplitudes, you get this kind of wavy behavior. But when you just integrate over it, like we did before, and just focus on the initial and final one and probability, and just this integrated stochastic matrix unit, then it's going to be different, right? This is going to be just this straight, like some kind of exponential instead, not some sinusoidal wave. So, but this was my attempt to actually, which is just following some old literature from 80s, how to formulate the stochastic mechanism so that the actual probability is also follows the density matrix. So we can know that the probability of being the definite probability of the particle being in definite state is the same as the density of the wave function, the pilot wave, right? And it's more complicated because it's not just like some static time independent matrix like we computed before. You actually have to compute it some like using formulas like that. I think it's like and you can compute a bunch of time-dependent matrices, I believe, like this. Like, so this is like I'm just drawing off-diagonal elements of those matrices, right? And they would just be used in some, essentially like a master equation, but now your matrix is not fixed like in the Hamiltonian because it was time independent before. We just, because this is just a single rotation, right? We just fix the angle and all that. We just rotate in a qubit, right? But now if you compute this I don't know how you would call it, even like some kind of transition rate matrix, then in the master equation it just acts as a Hamiltonian because it's time dependent. If you solve it, you at every moment in time your probability is exactly the same as the density matrix, and you can also interpret it in this nice hydrodynamic way. So what does actually different components mean, and you can recover what's like actually that it's due to some kind of osmotic pressure. When it's like my intuition was when you look at a quantum operation like this, right? If you look at the quantum gate applied to some qubit state, you can think of it as a kind of applying some semi-permeable membrane to some ensemble of particles, so that you can actually determine the dynamics of the ensemble of those particles as flowing through some kind of semi-permeable membrane. So that's what you have to do in order to describe the statistics of these particles on the left side of this membrane and the right side of the membrane. It's not just if you do just a single direction flow with no osmotic pressure. This is just a classical probability theory that you're doing, and you can simulate it on a classical computer very efficiently without any worrying about it. But in order to have a quantum computation, you have to have this backwards direction, which is due to this osmotic pressure, right? It's like osmotic pressure is essentially like a classic example is when you have some water, right? And you have a membrane inside this water that doesn't allow of transition of some salt particles. So if you have left side of your chamber, right, has more salt in it, it doesn't allow salt travel through this membrane, but because the concentration of the salt on the left and the right are different, the water moves to the other direction, right, in a different direction than the actual concentration of water itself. So it's like backwards, it moves along the salt concentration rather than the water concentration, so, something like that. I don't think I'm explaining it correctly, but yeah.
But in other words, so there's water and salt on one side and just water on the other side, then the water will try to the concentrations will try to equalize, so the side with more salt will like suck up some of the water from the left because the salt can't go through, but the water can.
Yeah, something like that. So in a way you can think of it like there's on the right side of the gate there's a water without salt in it, right? So, but it can be completely arbitrary state. Like for example, in the quantum Bayesianism interpretation, it's just you can think of it as a completely arbitrary prior distribution. So it can be initialized to any distribution, and then it just equilibrates after this osmotic dynamics. It equilibrates to the actual final distribution that you get after applying the quantum theory correctly, using all this conventional Hilbert space formalism and all that, right? So if you want,
is that your idea? Is that your analogy that you derived, or was that something in the literature?
No, it's kind of scattered. I don't know, like this osmotic analogy, I don't think it's too common. I couldn't find like a lot of references. Like I found like only like where I found this kind of formulas from this old from 1984 reference, which like about just discrete stochastic describe, but I couldn't find any other good example of this osmotic analogy and fluids. Even in hydrodynamic analogs, I don't think there's a lot of the analogies we apply in the semi-permeable membranes, because they usually deal with quantum mechanical systems, not quantum computational systems. I think that's the difference. We don't have much quantum computation examples described using these ideas. So I think that's the kind of thing that has to be changed. Right? So, all right. So, yeah, this is like a good picture in mind to have for this particular system. If you think of these ensembles of particles, right, you can think of the qubit itself. Now, if you also describe it like with the fluid, you can think of the qubit itself as just on a block sphere. You can just imagine all possible combinations. You can just sample uniformly all possible points on the sphere, right? And then if you have an actual qubit, you sample those points some kind of dynamically, just probabilistically you sample of those points, and then just along each axis, which is just the basis of this qubit, along each particular axis, it's either on this particular representation is either in the north hemisphere or south hemisphere, right? So essentially, like we are sampling across all possible directions, right? So that it's either rotating clockwise or counterclockwise. You can think of that, right? You just sample any direction, and if you look at it from some particular position, like in this particular example, it's like looking on it from the top, right?
Mm-hmm.
It's either, if it's blue, then it rotates clockwise, for example. If it's green, it rotates counterclockwise, right?
Mm-hmm.
So you can, and this is like a ensemble probabilistic picture of the qubit, because if you just have this values along every orientation, you can recover the actual vector by just statistics or tomography. You can call it even. It's like a qubit tomography. You can apply it. And you can, along every orientation, as before, you can apply the same kind of mathematical integration over intervals, so that there's along every direction there are different currents, and how along this particular orientation, what would be the probability of jumping or changing orientation along this particular orientation, how it behaves with time, right? So this is just me trying to show the exact same thing computationally, right? So just encoded a qubit by just this ensemble of particles, green and blue particles, and then you can apply along every orientation a different stochastic matrix, and so that you can resample along every orientation your of direction of rotation, and then that's essentially, and then apply the tomography to this ensemble to recover the final state vector, right? So essentially now we described how to apply a single quantum gate to a quantum qubit purely stochastically. Like we never employed any quantum amplitudes, density matrices, and unitary gates. We just have an ensemble of values, just blue and green values or something like that. We applied some stochastic matrix by sampling them with some probability, and we recovered the same dynamics that the actual quantum computation produces. All right. So, but this is the single qubit, right? So, any questions at this point? Okay, good.
Dugan, I don't know, maybe do you want to?
I don't know. Why are there gaps in the point cloud?
So there's not actually a gap. It's just it's when you see a gap, it means along this orientation and actually green, right? It's because it's like an antipodal point. It's either one point or its antipode is always lights up, right?
I see.
So along a single orientation is either green or blue. Okay. So if you have multiple particles, you essentially can encode them also in a similar manner. For example, this is like an arbitrary entangled state, and you can still sample all those points along every direction of the block sphere, and you can encode arbitrary entangled state also like as this ensemble of particles, just binary particle states, right? And which allows you even integrate entanglement into this representation too, because if you just show the block sphere as two vectors, you can't really represent an entangled state because you don't know how those vectors are correlated. But when you represent it as this ensembled binary states, and in a way, correlation is also encoded, because if you look along any particular direction in the block sphere, it's either like blue or red. One qubit is either blue or red, or other qubit one, and they can be correlated, right? Like maybe like this kind of picture is more helpful. It's like you can just project all the qubit to a two-dimensional plane. I was using some geo projection from the geo functionality, which can be useful. Just project it's like a sphere, so we project it to 2 dimensions. Now this kind of grids can describe arbitrary multi-qubit states, even entangled ones.
So just to understand check the understanding here. So you've got two block spheres. So are these two qubits, two different qubits, or how does it? What's the requirement?
Just a 2 qubit state, which is entangled. It's like a bell pair.
Okay.
Right. So let me see whether this works. have some dynamics here. Which maybe take a while.
And then
Load.
while it's loading, so is there something special about which axes are blue and red because they're entangled? Like, is that?
Well, maybe it will help if you just understand how those values are being sampled.
Okay.
How this, you can also think it's like a microstate of the macro state, because the block vector, the qubit state itself, which is described by a density matrix, right? You can think of it as a macro state in the usual like statistical physics terminology, right? It's a macro state, but this is like a microstate. So there are multiple microstates that constitute the same macro state. And so how do you sample each one particular microstate? You just take the actual probabilities. So if you take like a quantum state of 2 qubits and take its probability vector, right? This is just a four length probability vector. You sample from it, right? And then you just that's your actual samples, which you call, because there are 2 qubits, right? This is like being 0, 0. It's like both of them red. This is the probability of one of them being red, one blue, and so on. Right? So you sample from this probability distribution to get this.
Okay.
But because we sample it across multiple orientations, like along every orientation in space, because it's a qubit, you can also describe it as space nicely, right? Because you have a blob sphere, which is it lives in 3D.
Yeah.
Right. You can nicely kind of reverse this procedure, which is usually called a tomography, right? If you just have a bunch of measurements, even though these measurements are along all possible bases, you just have like a single measurement along every possible basis.
Yes.
Right. Usually by tomography, people mean like you have like just a few bases, like maybe along X direction, Y direction, Z direction. You have 3 bases, but along each of those you have a bunch of. Oh, look at this. you have multiple measurements, right? Like along Z directions you have 4 like 100 of actual outcomes along Z and also like that. But here you have just a single outcome along every possible direction in some kind of particular fine graining. So, but
can you make sorry to interrupt. Can you make those squares a little bit bigger? Because yeah, just zoom in a bit, because I think the resolution will be better for what we're streaming at, and then the one on the left as well. Oh wow, that's hurting my eyes now. Jeez.
Yeah, it's like one of those visual illusions. You know, it's like that tries to, one of those vision tests. It's like there's some kind of integer. If you don't see an integer inside it, you're blind. You're colorblind or something like that. Colorblind test.
Yeah, I was trying to see if I could identify some kind of like opposite pattern here. It seems like there feels like there's certain sections here where what's blue on the left is orange on the right. There's definitely some kind of pattern. It's not exact.
But if you see a pattern, then it means there's a correlation, so it's good.
Oh, okay.
If those were uncorrelated separable qubits, then there's going to be no correlation.
So the correlation is the entanglement to the degree that they correlated. What does the degree of correlation imply? Yeah.
Well, it's like an actual entanglement and how much those qubits are entangled.
So I thought qubits were either entangled or not. How are they partial?
No, there's a degree. There's a degree to it, how much they can entangle. The maximally entangled state, 2-qubit state, is a Bell state.
Okay.
Right? Okay. You can also think of it as a if you just like close one eye and look only onto the left grid. If it's completely random on its own, like disregarding completely the right one, then it's like completely means that it's completely uniformly mixed state. And when one qubit is uniformly mixed state, then it means it's like a part. It's like you discarded the second system that was pure, and that means that it's maximally entangled. In a way, it has the maximum entropy. the maximum, the uniformly mixed state has the maximum entropy, and when it's just 2 qubits, it also the same way as the entanglement entropy is the maximum.
So you could, another way to say it is there's information that's shared between these two states.
Yeah,
there is some
just
information.
by the nature of correlation between those different orientation. Yeah,
it's cool to do these experiments because it helps build intuition about like what is actually implied by entanglement and information and correlation and entropy. Just to like reframe it in these different visual kind of ways, it helps you like, or it's helping me understand a little bit more about like what quantum states actually are.
yeah,
it's very cool.
Yeah, I also enjoy like this alternative reinterpretations of qubits. Like I looked in all of them. Like this is like by far the most intuitive ones. When you just try to describe the qubit as just by a bunch of microstates and assume that there is some underlying statistical thing happens even below quantum systems. And what we are actually having by using the quantum theory is like using ideal gas laws either instead of an actual kinetic theory of gases. That's the difference in the analogy.
Next time, instead of orange and blue dots, you can have cat emojis and some kind of like emojis that was also very helpful from last time.
Yeah, cool. That would be like horrible here. It's like a lot of cats.
Okay.
Smiling. Yeah. Okay. Right. So this dynamics essentially shows how like this black dot shows the direction where you're looking at. It's like.
Can you make these a little bit bigger as well? Is that possible?
Yes. Yeah. So this is again like 2 qubits, the same 2 qubits, and you can just look how those, because again, if you interpret those colors as just orientations, spin orientation, actual spin orientations, it makes sense. It's like depending on from which orientation you're looking at, it rotates either clockwise or counterclockwise, right? And when it flips, the orientation is flipping is when it kind of crosses the spherical. I don't know how to call it, like I don't
hemisphere
know how to
or something.
Yeah, like if you try to move it, you see the flipping happens is like on the equator, right? Depending from which direction you're looking at. But it's still the same state, so the same microstate. It just kind of changes depending on from which orientation you're looking at it. Right, so it's the same microstate sampled from our qubit state, but it just changes depends on the perspective, which we call a basis also. So depending on the basis, different you have different, and this is the same for in 2D. It's kind of very similar to the usual geomaps. Those, if you move around, you can see the line that represents some great circle on it, the equator or something, right? If you don't move it around, you don't actually see it. It's actually just only seen in dynamics. Well, it depends. If it were completely mixed, then you wouldn't see it. But this maybe have some lines in there that are apparent because it's not completely maximally entangled state. Okay. What else do we have here? Okay, so this is kind of the same. Or yeah, so again, when you have multiple qubits and want to describe like this context that I was describing previously, how do you describe dynamics when you have these multiple qubits entangled with each other, right? And how to interpret this context that I called context of other values of all other qubits your qubit of interest is entangled to, and in a way it becomes complicated in a way. For example, if you have this 3-qubit state, right, which you just sampled a microstate from our actual quantum 3-qubit state, if you want to apply some gate, a single qubit gate to any of those qubits, you essentially have to consider all possible values along all possible orientation of other qubits it entangled to. In a way, it's like you can have to, because there are 3 qubits and there are 2 other qubits. For all of them, there are 4 different colors you can assign to each orientation, depending on what different values those 2 other qubits take along this particular orientation. So like this, like 2 qubits, they can take 4 different values. So for the first qubit, you along each orientations, you can assign 4 different values, 4 different colors depending on those values. And when you want to apply a gate to this first qubit, you have to apply it somehow independently for every color. So that's kind of how in this picture you have to interpret this context. And because it's like we have when you do this actual sampling by simulating it, it's always finite, right? So there's always finite number of orientations we sampled from, and it kind of becomes obvious when you increase the number of qubits, the number of colors also increase exponentially, right? And like if you have many qubits, you essentially have a single color per different direction. So a single color is not enough to recover the actual macro state along this particular context. So in a way, it's like becomes statistically your statistical noise increases with the number of qubits, essentially, because you won't be able to recover the state and to apply all this integration as we did in order to determine the current, in order to determine the stochastic matrix along this particular, using this particular context of other qubits, right? But when you are not entangled, you essentially can kind of ignore this, which is like not obvious how you can determine it. You can approximate your entanglement degree of this particular qubit to other qubits by just because you assume that your whole multi-qubit state is pure, right? Which means for the whole system, it's pure and it has maximum information and the minimal entropy, right? But when you just focus on a single qubit, how much information it contains determines how much it is entangled to other qubits. So that's in a way can determine locally how much actual fine graining and how much context one needs, right? In order to apply the stochastic mechanism, in order to simulate its dynamics. So it's I know it's very complicated. I don't understand it myself, but it's like, well, I understand how it works, but explaining it is it's like on a completely different level. But you get the idea, right?
I'm trying to get the idea, so maybe I can rephrase in that so we can get closer to figuring out how entangled ideas can be stochastically equivalent. Okay, that's probably the wrong phraseology, but okay, so in this example at the bottom, there's 3 qubits, and is that why there's 3 different colors? Or how many different colors are there?
So there are 4 different colors.
4 different colors, okay.
So there are 4 different colors because, for example, as I was describing, if you just focus on the first qubit here, right? Along each orientation, which is just a single position of the dot here, depends on definite value along this orientation of other qubits. Because 2 other qubits.
Wait, but why are you clicking at the top one? So are there 6 qubits in the system?
You can, because it's this is just shows individually. Yeah, like ignore this for now.
Okay.
It's just like if we ignore this one.
Okay.
It's just that's what you have to do if you want to describe the first one. And
okay.
Correspondingly, if you want to describe the second one, you like only zoom on this one and
those 2. Okay.
In the context of these 2, right? So this determines the context for this qubit.
Okay. So that qubit is a mixed state of the first 2 qubits? It's the quantum state of the 2 qubits at the top.
Well, you have just a 3 qubit state, right? Like we had here, right? Like this. So let me copy this to the here. So this is like 4 different values, and that's why there are 4 different colors, because there are 4 different contexts that this qubit lives in, because there are 2 different other qubits, right? So if you pick like one position, arbitrary position, and you look at that position along this position orientation what the value for other qubits. It can take 4 different values. So it can be red, 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 blue, blue, red, blue, blue.
Yeah.
Right. So there are 4 different values. So that's why we can just assign it one of 4 different colors.
Sure. Yeah.
And then like if you just select a single color points, only the single color orientations for this qubit, and then estimate the actual quantum state for just this color. It's like estimating this state. Where did they put it? It's like estimating this state in the quantum circuit. We just fix the color. It's like putting those heads, bra heads on the other qubits. It's like determining the color. And because there are much fewer points to recover this state from this ensemble, the quality of that state drops with the number of qubits. Okay, so that's kind of can be how the complexity of quantum computation can be described.
When you say the quality, you mean like the quality of the information that basis can give you the probability of the state?
What I mean by quality is essentially how precisely you can determine the block vector if you give just the samples from finite number of orientations. Right? If you just give me one sample from one orientation, you can't really recover the block vector precisely because it's not enough statistical power.
Yes,
right?
yes.
You have to like put many points on the block sphere to actually to determine the vector. You have to average them out. Right? But the number of points along each context increases with the number of qubits. And so that's where the whole quantum complexity is coming from in this particular representation. Right? So you either increase the number of points, increase the number of orientations in your ensemble, which has also you have to increase it also exponentially in order to kind of keep up with the complete statistical power of this ensemble along all the qubits. Right? But maybe I'm still thinking maybe there's some classical algorithms that kind of tries to prune it based on the, as I said, like if you just look locally on this qubit and you just estimate how mixed it is, you can say how entangled it to the other qubit, and so maybe you can determine some nice way of actually recovering the local states, maybe not for all of them, maybe some kind of, just do a better job at it, right? Just based on how entangled it is.
You run like a little machine learning algorithm to like figure out based on where you are, like what the probability is
I don't think machine learning is required here. Just looking at one single qubit or 2 qubits together, you can pretty simply determine how mixed they are, right? And that will determine how they entangle to other qubits. If they're completely entangled, maybe then it doesn't matter what gate you're applying to. So there's a nice balance between if it's completely mixed, right? Then applying a gate to it doesn't matter. You can just ignore it essentially. But if they're not mixed, then it means they're separable. Then you can just ignore the context altogether, right? And then estimate the gate, ignoring all this context, take all the colors, all the points, all different orientations, estimate the state, and then resample those ensemble points locally again.
Okay.
So in a way, there's like some classical algorithm there, which is not specified yet. But I think there's a nice idea for the classical algorithm for simulating quantum computation is there, so that you have to this.
So that's important to remember. It's important to remember the motivation here is quantum computation. So we're trying to actually get a way to compute with these things. So that's why, like, whether it's completely mixed or somewhat entangled, less entangled, and there's some kind of probability associated with the state, that's what allows operations through gates to actually provide computation, something like that.
Yeah. Let me like remind you the usual problem with the quantum computation, why it's not, it can't be simulated on a classical computer efficiently, right? Because usually if you have an arbitrary quantum circuits or some implementing some quantum algorithm spanning over 100 qubits, thousands of qubits, maybe million of gate deep circuits, right? It's computationally infeasible to simulate it precisely on a just manipulating vectors, because your vectors are huge, right? If you have hundreds of qubits, then your probability vector, the state vector, is 2 to the 100 size.
Okay.
Long vectors, right? So we can't really manipulate them efficiently. So there are different classical, there exist some classical ways of manipulating them, like maybe pruning around some higher rank tensors and all that, contracting your tensor network more efficiently. Like this is just another, I think there's another approach to just effectively perform this kind of pruning by just looking at how actually this ensemble evolves with each gate application, right? Because that's the actual problem. If you start, your usual quantum computation starts with a purely separable state, so we can resample each of the qubit independently, right? So you can have like just completely dependent ensembles, microstates of each qubit. Then you apply gates to them, either single qubit or 2 qubit gates at most in practice, right? All of the circuits can be formulated by just 2 qubit gates at most, right? And when you apply 2 qubit gates, they can you need to perform some local operations to those ensemble, right? And this local operation has to be somehow estimated. Nice, yeah, nice balloons from nowhere. Okay, distracted me. Yeah, so.
Okay, so I mean, like what's nice of this is a visualization of why trying to simulate quantum computing in a classical way becomes computationally explosive very quickly.
Yeah, and I'm just thinking how because the hope is maybe we don't need quantum computers, right? Maybe there's actually general classical simulators that can effectively simulate all the quantum algorithms efficiently on a classical computer. And maybe we just have to look at the different approaches how to do it. And this is just purely statistical ensemble-like approach. What to do to qubits probabilistically locally, how to determine how to do these operations, how your quantum operation, quantum gates correspond to those operations. You don't even have to do those integrals that we did. All you have to do is to determine, in practice, all you have to do is just to determine the initial and final probability distribution in all of those different contexts, right? That's the only problem. Because if you have many qubits, there are exponentially many contexts. But maybe you can prune those depending on how actually mixed your state that you're acting on right now, somehow.
I see. I'm starting to figure it out. Okay. So it'll be interesting. It doesn't need to be totally efficient. It just needs to be efficient enough where you can just like not have to build an entire quantum computer to do some quantum algorithms.
Yeah, so if you just have a bunch of samples, can resample to every gate. You can like naturally parallelize them. It's like whatever, how many samples fit in memory on a single computer, right? If people now train models using thousands of GPUs, maybe if you want to simulate multiple qubit quantum algorithms with the same number of just like holding samples for each qubit on a single device. It's like how many fit in there. It's not exponential, but still huge. Maybe it's like given 100 GPUs and like just storing all those samples on a single one for every qubit. Maybe you can do something. I don't know. It's like just wonder how far this kind of computation can get you.
Interesting.
how it would compare with the like current state of the art. Maybe on the supercomputers that can precisely simulate like 50 qubits. Maybe with those different pruning techniques, maybe even 100, but I don't know. Maybe there's some different trade-offs though. Here, maybe there's also some different trade-offs. Who knows?
Very cool.
Right. Oh, there's more. You know. So, do we want to go further?
Yeah, I think let's round it off and go through what the rest of this is. How much where are you in terms of percentage of the notebook? 30%. Yeah, that's perfect. Oh, I want to see the pictures. Yeah, let's not skip over these cool visualizations.
Maybe I can just explain those pictures. It's like without explaining like the whole phase space.
Because you briefly did discuss this thing before, right? The tetrahedron.
Yeah. No, let's try. So the way we described a qubit before, right, with just a single vector like that, you can also just describe the same qubit using just a probability vector in 4-dimension, like corresponding, for example, corresponding to measurements symmetrically along those vertices of a tetrahedron. So you just take those 4 different orientations pointing on different vertices of the tetrahedron. This would pick a nice symmetric basis set, measuring in which your probabilities fully describe the same probability vector. So in a way, you now encode your probability vector purely probabilistically already, without like having this spatial direction or amplitudes or density matrix. You just encode the whole density matrix as a 4-dimensional probability vector from the start, right? And you can already, it's much natural to describe all of the computation in these terms. Now you don't have any complex amplitudes, you just have probabilities, but the things that change is the operations, how operations on those qubits differ from classical probability theory. In a way, we were trying to compute a stochastic matrix, for example, right? But these probability vectors and unity transformations would correspond to quasi-stochastic matrices like this, right? This is like some, I think this is not a quasi-stochastic, this is a transition rate matrix. But whatever, the fact that it's not classical is that it has this particular one because it has negative components along off diagonals. I think the transition rate, the logarithm is allowed to have negative on the diagonal, but the off diagonal has to be all positive. Whatever. It's just it's some kind of non-classical probability manipulation of a probability vector, which is like what distinguishes the quantum gates from classical gates on the probability vectors, right? And that's how you can, so explaining those using the same kind of formulation like before, you can also apply the same kind of ideas of computing the probability current. It actually has a much nicer formula. So given this transition rate matrix of you can just compute the current by just using this, but just value of this matrix and the probabilities of being in final and initial and final states, right? You do the same kind of truncating the current so that it's always positive, but it actually always stays. It's also much nicer in a way that it's always fixed in sign, right? It's either always positive or it's always negative. Which is like I never proved, but I don't. But it seems like this way. But it wasn't obvious. I still don't know why. But it's just if you just generate a random unitary transformations, their current in this phase space always fixed in size. Fixed in sign. It's always positive or negative. So in a way you have to. So there's no like crossing the sign like we had in the qubit state of 2 values, but now you have 4 different values, not 2 values. So in a way, in this sense, it's more complicated. So now a qubit is jumping around between 4 different states instead of 2. So you can't really integrate it precisely, right? Unless I don't know how to set up the same kind of integral, but you guys nevertheless can still simulate it. So in a way, what you have is essentially, I never wrote it here, but essentially like a time-varying Markov chain problem. Right, so you have 4 different states, like the size of those vertices correspond to initial probability of being in that state, right? And it's time varying, showing the time varying probability of jumping from that state to another state. So it changes in time, right? So in a way, if you want to simulate this time varying Markov chain, you just have to sample those 4 states, and then at each moment on the time interval, the probability of jumping from that state to another is different. So if you simulate it, you can recover the whole quantum statistics from it. You can recover how this probability vector evolves, even even with the quasi-stochastic matrix, because it's like it's not clear how you use it in order to just resample your states. But now, if you formulate it in this way, you can, right? And you can just resample a bunch of trajectories, which was exactly would correspond to those Bohmian trajectories in quantum mechanics. But now they're discrete. It's just a bunch of, this is just ensemble of different trajectories that particles take essentially from different states, and they're jumping around at different points in times with some different probabilities. So we can sample a bunch of those trajectories, and from those trajectories you can recover the whole statistics of how this probability vector evolves in the space, right? So that's how you can describe the dynamics of the qubit. All right. So this is just I can go into this quantum Bayesianism thing, which is like a has nice properties when you think, because like I was trying to describe it using just there's some manipulation of the probability vector happening, like exactly like this. There's some matrix, right? This is like a probability vector, so you have this master equation essentially of how the vector evolves. You can, it's like if it's even time independent, so we can exactly solve it, right? So that you have a stochastic matrix and your initial probability vector, and you can compute the probability vector at any moment in time. So that's how quantum gate is applied to the quantum state in this phase space. But this quasi-stochastic matrix it's stochastic matrix because it's like it's 4x4 because it's a phase space, but it's stochastic because its rows and its columns sum to 1, like the usual stochastic matrix, but it has negative elements. Right? So that's why different in the quantum case. You have to deal with quasi-stochastic matrices in the master equation, in the solution, and the equation itself. Right? So you can't really treat it as a conditional probability table. That's how you would treat it in the classical sense. It's just some conditional probabilities, and if you want to resample your ensemble of states to a new state, you just pick those conditional probability table entry and resample your every state using those probabilities. Like you just pick the column, and this would describe like if your state is the second. If your definite state is in the second state, a definite particle in the second state, this is your probability vector of conditional probabilities that you have to use in order to resample to get to the new state. But even if it has a negative value, you don't know how to do it, right? There's no procedure to how to just, right? You have to kind of somehow to incorporate all this destructive interference of probabilities, and that's what is complicated, right? But nevertheless, you can still do it but if you just want to compute the dynamics, you just multiply the matrix by a state and it works. You still get the probability vector from the probability vector, right? But not all of them. But the point is that you can also, this is just, I was explaining it earlier at some point already, how you can also naturally think of those quasi-stochastic matrices as those negative elements having some inference component to them. In a way, your forward stochastic component is your natural conditional probability table component that you use to resample things, right? But those negative components, they have this inverse effect. In a way, you have to infer or perform an inference of some probability vector, unknown probability vector from your evidence or something like that. So essentially, you have to perform, because that's where the quantum and just Bayesian rule comes from, because that's the way how people inverse conditional probability tables in usual probability theory. If you have a stochastic matrix or conditional probability table, its inverse has negative elements, right? Also, if you already have some negative elements, your quasi-stochastic matrix, if you inverse it, it's gonna have positive ones. So in a way, you can decompose your quasi-stochastic matrix as this product of forward and backward components, when all of those F and B are both stochastic matrices, right? But the inverse of B is quasi-stochastic. So that's where the negative components in S comes from. So after you decompose it, you in a way you get some matrices, but you can like use F to just classically resample your ensemble, right, without no problem. But then your Bayesian part comes from the fact that you have to do this in reverse, right? Then that's what is called inference, and you have to apply some form of the Bayesian rule in order to infer your probability vector from some given prior whatever. Given that whatever you sample after the forward step is your evidence, you treat it as some kind of data coming to you, right? Some kind of, then you have to estimate some actual. You already know the model. That's the machine learning analogy. You have the data, the exact data, right?
What is the model?
Maybe coming to you like from it's either a probability vector or an actual sample, but you have the model, which is also exact. You know the B, right? But you have to estimate what will the probability vector that after applying this model gives you the data, right? You're estimating the parameters of your model, something like that. Yeah. This is like this is the Bayesian rules. This is like the likelihood the prior can be different, right? You can start from different priors, and the point is that the actual vector, the probability vector that you want to get, that you get after applying the gate, is the posterior, and you have to, in order to estimate it, you have to apply the Bayesian rule multiple times, like iterate it over, and that's what this picture shows you. It's like this is because we're dealing with 4-dimensional probability vectors. Because the normalized, you can drop one of the dimensions and you can embed it in 3D now, right? Because they're sum up to 1, so they're just 3 degrees of freedom. So in a way, so now this is like a probability simplex now. Every point here represents different probability vectors, 4-dimensional probabilities.
Can we zoom in on this and restart? So now that we've got a visual, maybe I can start following with better clarity. Okay, can you make it a little bit bigger? And then let's look at those cool little lines that are flowing through there. Because is there a direction to those lines? Are those arrows? Okay.
Yeah. Yes, those are tiny arrows. They have a meaning, and those like the initial points of those arrows correspond to priors. Okay. Those are like a prior vectors you can pick at random, right? Each tiny arrow is an application of the Bayesian rules, of the Bayesian rule once, right? I think red point is just here to show the actual initial vector or the evidence. It doesn't actually visually controls the dynamics of those arrows anyway. It's just there to have it there. But the point of convergence is that essentially, given some initial prior, if you apply the Bayesian rule multiple times, you converge to the same posterior. And that's the actual probability vector there. And that's what the quantum dynamics produces in the end. So you can think of you have to, or those osmotic pressure or whatever I was describing previously, is this fact of converging from arbitrary initial condition, which is your prior, and by some osmotic velocity, it converges to a different point. And that's the actual probability vector that you observe at the end of applying your quantum gate. Right? In phase space or not. Kind of can apply this intuition in both. But in phase space, it's 4-dimensional, which like normalized and can be embedded in 3D nicely. So you can pick any prior vector and just evolve it using the Bayesian rule to the prior. And this probability vector is the result of applying a quantum gate. I don't know.
So is there an analog for this in a block sphere? Could you do this in like a block sphere?
Yes. You can in a way, yes. You can do the same thing there.
And then would be the position would just...
Yeah, there's like a natural linear transformation from these points to the sphere. In fact, maybe I have some visual.
And then the position would be the direction of the arrow thing in the middle, something like that.
Sorry, what direction?
What's the arrow called in the block sphere that's pointing in a specific direction?
Well, there's some center. I think in this case, I don't know. It depends how you project it. But there's some point. There's some point in here that corresponds to the center of block sphere. right? If you want to, I think it's like here, right?
Isn't it the red? Oh no.
No, the
it's
red one is
different.
just the actual vector or quantum state that you get after applying only the forward part.
Yes, I see. Yeah.
Like this, right? So you apply. This is like, and this kind of drives the dynamics of all those arrows from arbitrary priors. But if you want to project it, and maybe I should have done it. Like this is like maybe the center of the block sphere. So there's a vector here. This is a quantum state. So this is another quantum state, right? So essentially, like every point here is some quantum state, right? And it just shows you how it involves.
We put it in a block sphere.
Or maybe not all of them are allowed. I think that's the point. Maybe there's some subset of it over valid quantum states, because they're not all probability distributions are allowed in a way.
So would that translate to what would be inside and outside of the tetrahedron?
No, they're always going to be inside.
Okay.
Right? Is that every quantum state corresponds to a valid probability distribution, right? But not every probability distribution corresponds to a valid quantum state. It's like I'm pretty sure there's just some inscribed sphere in this tetrahedron that is the block sphere. Something
Okay,
like that,
okay, interesting. So it'll be outside of the block sphere itself. That'll look pretty cool. Could we render that?
Well, I have a bunch of like, well, it almost looks like already like this. It's just a differently shaped tetrahedron, but it's something like that. It's just
then you'd have those things going into the. Would they go to the tip of the arrow? That's what I'm trying to say. Like, what is the arrow? How would the arrow correspond with the quantum state?
Do I have some nice? It's like in 2D. It's like looks like this. I think. They also had them. This is like a 3D version. I should have some. Well, maybe this one is like this.
Okay.
Yeah.
Okay. I see what's going on here now. Just spin it around a little bit more. What type of triangle is that? Is that the same shape of triangle as this one? Tetrahedron, sorry.
No, it's not the same shape, because in order to produce this one, I just dropped one of the components of a 4-dimensional vector, right? And that's happened. That's what happens when you do that. But in actual projection here, right? It's more natural. it depends how you project this 4-dimensional thing to 3D. It's a bit varies in how you can do it.
Interesting. Okay, cool. So let's see those other versions down here. They're quite interesting as well.
Yeah, this is like it's like a different way of doing it. Actually, completely different. It's
okay.
It's like here your arrows show the application of a single Bayes rule, right? But you can actually compute the likelihood, because we already know the likelihood here. In some sense, right? You can compute the likelihood exactly and instead follow the gradient, and it's like a completely different dynamics, but that produces the same results, which in a way tells me that Bayesian rule may be not even the most natural way to do the dynamics in this phase space to describe it. Like here, it's like the actual difference between them. It's like if you start from the same prior, if you follow the Bayesian rule, it like follows a completely different trajectory. They all end up in the same posterior, but whether you follow the Bayesian rule or the gradient of your likelihood are completely different. Right? But this is just a probability theory stuff, I guess. But this thing wasn't obvious to me. On its own, it's just a classical thing without any quantum relationship whatsoever. But the point is that the Bayesian application of Bayesian rule and following the likelihood gradients is just different dynamics, and it's not obvious which one is correct. right? And whether if you actually trying to describe the quantum dynamics using it, maybe it's even experimentally comparable. Who knows?
Can you spin the top one around a little bit and make it a bit bigger? And what do the colors represent? The speed or the gradient?
Yes, the speed. Essentially, it's slowing down towards the end. The same way as the Bayesian rule, the size of the arrow also.
Oh, I see. Okay,
so
okay.
They both slowing down when they approach the posterior, but they still have the same point. They still converge into the same thing, but differently.
So is there something about the fact that all these arrows are starting from the surface of the tetrahedron, or is that not the case here? It just looks like that.
No, it looks like a vector field in the volume.
Yeah, well, different points there.
Oh, okay.
It's like it just decided on some nice distribution of points where the arrow starts, right? But the beginning of arrows are sampled uniformly or something like that across all of those in the region. This is just twin plot 3D here, right? So it's like literally just if you know the form of the likelihood, take the gradient and you can plot it using the vectors.
Got it. Very cool.
So what else do I have? Yeah, this is just a comment about that you can do this decomposition in a different way. You can either, in a way, it's like related to either you decompose the stochastic matrix itself, which is like a Lie group kind of way, or you do it in the exponential, which is like a Lie algebra like space. So either you decompose in the group or in the algebra domain, and you can get different things. Like if you do it in the algebra, there's some problems. No, there's no problem, but there's a precision problem. I think the decomposition was so that you have to apply more. I think I have it at the end here. Yeah, and so this is like comparing how to decompose. If you like decompose how I did using the forward and backwards of the stochastic matrices, you get like almost immediate convergence, right, to the posterior. But if you do it in the exponential, you decompose it in plus and zero components, and then you exponentiate them to get forward and backwards. You get very slow convergence instead. So this is like, it's like you don't even see it in comparison, but it still goes to the same destination. It's like because you essentially like have almost uniform matrices, like they almost have the same values, and the difference of actually changing it's like very tiny, so that's why it's slow. But unless you can go like exponentiate and take logarithms back and forth between them, so it's like the problem is that it's very slow in practical sense, but because it's naturally described in infinitesimal, so because it decomposed in the algebra domain, it's more natural there. Because what we've done previously by decomposing the stochastic component, if you exponentiate those, you not necessarily produce the nice transition rate matrix. It's not going to be valid, right? But if you, in a way, yes, in a way, you have the stochastic way. Stochastic matrix is like a conditional probability table. If you exponentiate it, you essentially compute the transition rate matrix, right? So in a way that you can decompose either the conditional probability table or the transition rates, and depending on which of those you decompose, you get different behaviors. There's some trade-offs, so I don't know. This is like, I haven't explored it too much, but in a way, the transition rate matrices are decomposed naturally because they correspond directly to the fluid stance and velocities. I don't know what this is doing here, right? This is like the exponential. L is what I call the exponential of that stochastic matrix. It's a transition rate, which also corresponds to the Liouvillean in the into quantum sense, in the quantum case. So it's more naturally related to the quantum case more directly.
So
and if you decompose it into these two components here,
yeah, what happens?
yeah, those are kind of some intuition in this fluid analogs, right? Those different components of this transition rate, and those that actually do behave like classical transitions. But because one of them is negative, you interpret this one as a osmotic part, which is like going backwards, right? And one is interpreted as a forward direction, right? So it's like velocity. So like this is v, this is the velocity of the actual fluid. It's either going forward or the backward during the due to osmotic pressure, and this is like correspond. This is like this decomposition of the transition rates, quasi-transition rates correspond to. So if you do this time, those would be the natural classical transition rates.
Got it. So what you're saying is instead the Liouvillean quasi-transition rate matrix can be decomposed directly to circumvent the embedding problem, which will also be analogous to separation of streaming velocity of particles in the quantum fluid into its forward and osmotic parts.
Yeah. Yeah.
Got it.
I should read whatever I wrote instead of coming up on the spot. Whatever I meant. Yeah.
Very cool.
Yeah. So the embedding problem is this. Is that when you decompose your stochastic matrix into this forward and backwards part and take the logarithm, which should correspond to the transition rate, but it's not going to correspond to one.
Wait, can you explain that again? What's the embedding problem?
Oh, trying to remember. For some reason, hold on. I think they don't sum up to one or something. No. Here's already fixed.
But if we take not the most negative.
Yeah, so this is like if you just take the logarithm of the f and b, you still get negative values on the off diagonals.
Okay.
Right. So that means that's still the quasi transition rate. It's not a classical transition rate. Yeah. So that's what the embedding problem is all about. If you just take naively the logarithms, you don't get the nice transition rate.
So why is that a problem? Like we're taking the log normally, not. Wait, I still don't understand that part. What's being embedded here?
Well, the embedding is you basically what in the exponential is the matrix that you use in the actual master equation, right? Is the one that in the equation that you solve in order to get probability vectors at any point in time, right? But when you exponentiate it, you get the solution directly, right?
Yeah, okay.
So in a way, the problem is about that they don't correspond to each other. If you just already decompose the solution and try to come up with the matrix that is part of your equation, right, you get some not classical things.
So that mass equation is not allowed to have quasi-probability matrix.
No, the equation is allowed to. It's just if you want to simulate it, you can't really classically do it.
Okay.
Right, you can solve it.
Okay.
Right, but yeah.
That wouldn't.
The solution is just like dealing with numbers. You can still exponentiate some non-classical transition rates, but if you just have the solution, which is classical, and you just try to come up with this matrix, it's not going to be classical, right? There's like one way of solving it is just coming up with some giant shift, right?
But there's no guarantee that shift is enough.
No, I think that's not the problem. You get the same problem as like of the precision thing. If you make this giant shift, those F and B's are going to be again look like this, very uniform with the slope convergence.
Okay, I see.
Right.
So that was actually maybe important to explain. So what you're doing here is a different way to circumvent the embedding problem. Is by
that was different. If you decompose directly the solution to the master equation, right? You can supplement it by just in the decomposition just apply the larger shift, because the decomposition is just shifting all the negative values away and then normalizing it to get the stochastic matrices. But you can just increase the shift, and you can, so that the logarithm still yields the nice transition rate, the classical one, right? You can do it, but it's unclear what would be that shift, right? It doesn't fix it, so it's just it's not unique. But if you decompose in the exponential the same matrix that is in the equation, right? You just decompose it using not as a product of matrices, as some sum with the forward and minus osmotic things. You can directly decompose there like this, and then it's more natural. But as a result, you get some practical issues. But at least it doesn't have arbitrary parameters.
Interesting. So, I mean, doesn't this have application to quantum circuit simulation in classical computers then?
Well, as you can see, we can do an analogous simulation, because you have the same kind of problems as we had like with this simple picture here, right? You get the same kind of problems there. It's just you have now, instead of 2 colors, each color is going to have 4 colors because we are now in phase space. But you can apply the same kind of ideas there. But you don't have to assume multiple orientations. You just pick the orientation of a tetrahedron, fix it, and you resample those. And those samples is enough to reconstruct the state, right? Statistically. If you just sample along a simple axis, simple basis, just like 1, 0, 1, you can't really recover the arbitrary quantum state, arbitrary block vector. But when you pick the tetrahedron and you sample it between 4 different states, you can recover them. You don't have to. So in phase space, you can perform the same kind of statistical dynamics on that representation. But you have 4 colors instead. You have the same kind of context problem, which just also increases much faster, still exponential, but now you have 4 in the power of number of qubits, not 2. So in that way, it's much worse, but who knows?
Very cool. Oh, thanks for that. That was a nice rapid exploration through Bohmian mechanics and into Bohmian quantum computing potential. Interesting implications. Bohmian quantum computing. Interesting.
We actually like computation more than computing. For some reason, we try to use computation term because it's like more general, rather than computing that involves actual hardware and all other. It's not very theoretically inspired term, I guess. I don't know.
Makes sense. Dugan, any questions from you on that?
No. Good.
Very cool. Okay, thanks so much for that one. We will do some more live streams in the coming week. We had a cool happy hour get together yesterday on the Discord server, so that's something we'll probably be doing a few more of, and maybe including some activities. And at some point, I'm sure Stephen would like to engage with the community as well on a more frequent basis. So if you are looking to be part of the community, I suggest just start engaging with the channels on the Discord server. Show us what kind of work you're busy with, and there's potential application to join us as an affiliate researcher, which is a new role that we're going to be making official in the coming couple of weeks. So stay tuned for that. And yeah, we're looking for people to contribute in any of the thematic areas that we are doing research. So whatever level you're in, either as undergrad, postgrad, or even high school students, if you're a promising high school student that's got the ability to create interesting research content, reach out. And our new website actually has a form you can fill in on the About page. to apply as a field researcher. So that's like an exciting development. And yeah, we look forward to seeing you guys on the Discord and on YouTube soon. Okay, that's all for now. Bye.